Here's something that almost nobody is talking about loudly enough. We are in the middle of an AI boom, and this boom is eating electricity at a rate that is genuinely hard to wrap your head around. Data centers globally consumed around 415 terawatt hours of electricity in 2024. That is roughly 1.5% of all electricity used on Earth. And by 2030, that number is on track to nearly double. We're talking about the power consumption of an entire country, just for servers running AI. And here's the thing, this isn't just an inconvenient line on a graph, it's an actual ceiling. You can't scale intelligence infinitely if the power grid can't keep up. The cost of running these models is enormous, and the infrastructure is straining, all while the situation feels like we're sprinting towards a wall at full speed with no plan to stop. But there might actually be a way out. A startup called Extropic thinks they have built something that could fundamentally change this equation. A chip that claims to run certain AI workloads 10,000 times more efficiently than a GPU. But the physics behind it? What are they? Well, that part is genuinely fascinating, and it starts with a law you probably heard about in school. Now here's the uncomfortable truth about computing. It has a physical cost that we cannot engineer away. Every single time a processor handles a piece of information, energy is consumed and released as heat. This isn't a design flaw. This is the second law of thermodynamics telling you that any process involving information has a physical price tag attached to it. For decades, we have been able to essentially cheat this by making transistors smaller and smaller. Smaller transistors switch faster and burn less energy per operation. Now that's been the engine behind Moore's law, doubling the number of transistors on a chip roughly every 2 years. But those greens are slowing down. We're approaching physical limits where you simply cannot cram more transistor onto silicon, and the energy cost per computation is not going to zero. It has a floor, and we're getting very, very close to it. Now, to understand why what Extropic is doing matters, you first need to understand how traditional chips actually work, and why they are fundamentally mismatched for AI. A transistor works like a switch. That's it. You push enough voltage through it and it flips on. You drop the voltage and it flips off. Engineers have spent 70 years perfecting this behavior, making sure these switches are as clean and as reliable and deterministic as humanly possible. The whole architecture of modern computing is built on this. Bits that are rock-solid ones and zeros, operations that produce the exact same result every single time with no ambiguity and no uncertainty. That is great for spreadsheets. It's great for loading a web page or processing a bank transaction, but AI doesn't work that way. AI is fundamentally probabilistic. When a language model generates the next word, it's not doing a deterministic lookup. It's working with a massive probability distribution, weighing thousands of possible outcomes and sampling from that distribution. Now, when a diffusion model generates an image, it's gradually pulling structure out of noise, step by step, guided entirely by probabilities. So what happens when you run AI on a deterministic chip? You end up doing enormous amounts of precise, exact matrix multiplication just to approximate something probabilistic at the end. You are forcing a perfectly rigid machine to fake randomness, and it costs a tremendous amount of energy to do that fakery convincingly. But what happens when you let the voltage drop? This is where Extropic's insight is genuinely brilliant and a little mind-bending. Stay with me here. In traditional chip design, engineers run transistors well above the threshold voltage needed to keep them stable. You give the transistor a strong enough signal that it snaps cleanly to 1 or 0, and it stays there. The whole point to completely overpower any natural noise or randomness in the circuit, and there's a lot of that noise. Electrons are jittery, heat causes fluctuations at the atomic level, and every transistor in your processor is constantly being bombarded by thermal noise, and your chip is spending a big chunk of its energy just fighting that noise to maintain stable states. Now, what if you deliberately turned on the voltage down below the stability threshold? What if you let a transistor operate in what's called the subthreshold regime? Something interesting happens. The transistor stops being a clean switch and it starts flickering. The thermal noise that was previously getting suppressed is now strong enough to randomly flip the transistor between states. The transistor becomes inherently unstable, probabilistic by nature. To a traditional chip engineer, this is a nightmare. Your transistor is no longer reliable. It doesn't give you a predictable output. But Extropic looked at this and said, wait, that's not a bug. For AI, that's exactly what we need. This chip is built after the realization that we don't have to fight randomness. In fact, we can use it in our advantage. So that unstable transistor becomes the foundation of what Extropic calls a p-bit, a probabilistic bit. Unlike a normal bit that's locked at a 0 or 1, a p-bit randomly fluctuates between the two states, driven by thermal noise, and crucially, you can tune the bias of that fluctuation. Apply a certain control voltage, and the p-bit spends more time in the one state. Shift that voltage and it spends more time at 0. You're not forcing it to be 1 or 0, you're shaping the probability that it will be. This is the core reversal. Instead of burning energy to suppress physical noise, you're harvesting it. The randomness that nature gives you for free, the jittering of electrons caused by heat, is now doing computational work. You're not simulating probability on top of deterministic hardware, you're building hardware that is probabilistic from the ground up. And the energy difference between doing all that matrix multiplication to approximate probability versus just reading what physics already hands you, that's where the 10,000 times efficiency claims comes in. You are genuinely doing orders of magnitude less work to get the same result. Now, when it comes down to connecting p-bits, a single p-bit isn't particularly useful on its own. The power comes from connecting many of them together into a network, where each p-bit's behavior influences its neighbors. When you configure the connections between p-bits to represent a specific probability distribution, or an energy-based model, if you will, something remarkable happens. The system naturally settles into low energy states, and here's the key, this is framework. Low energy states are the most probable states, the most likely answers. This behavior comes directly from the Boltzmann distribution, a foundational concept in statistical physics that describes how physics systems evolve towards their most probable configurations. You're not calculating your way to an answer. The physics of the chip is finding the answer for you by literally relaxing towards it. Extropic calls this hardware a Thermodynamic Sampling Unit, or a TSU, and the name is deliberate. This is not a process unit that steps through instructions, it is a sampling unit. You give it an energy landscape and it samples from the resulting probability distribution using the natural dynamics of physics to do the work. The Z1 chip, their first production scale version targeted for 2026, is designed to pack hundreds of thousands of these p-bit circuits on a single chip and potentially millions across a multi-card system, all built on standard silicon, with no exotic materials and no cryogenic cooling required. Now, I want to be honest about the challenges here because this is where a lot of tech coverage falls flat. The physics is definitely elegant, but engineering at a scale introduces real problems. For one, analog circuits are sensitive. A normal digital chip doesn't care if the temperature shifts a few degrees or if a transistor ages slightly because the logic is designed to be robust against small variations. But these p-bit circuits are intentionally operating in the messy regime where physics governs behavior. That means temperature changes, manufacturing inconsistencies, and component aging can all cause drift in how p-bits behave. Managing that at scale across hundreds of thousands of circuits is genuinely hard engineering problem. Unwanted coupling between neighboring p-bit elements is another real concern. If adjacent circuits are influencing each other in unintended ways, your probability distributions get corrupted. And then there's the software problem, which might honestly be the bigger challenge. The entire mathematical language modern AI is written in assumes computation is a sequence of deterministic matrix operations. A TSU doesn't do any of that. You can't port existing models to it. You have to redesign them from scratch into a mathematical framework that almost no working AI engineer uses today. THRML is Extropic's attempt to start building that bridge, but until it's as mature as PyTorch, the hardware could be physically perfect and still be practically unusable. But here's something I appreciate about Extropic's framing. This is not a claim that replaces everything. Your bank's transaction processing system will still be running on deterministic silicon. Your operating system? The same. Any task that requires exact, repeatable output stays on conventional hardware, and that's correct. Where thermodynamic computing shines is specifically in probabilistic workloads. Generative AI, such as image generation, video synthesis, language models, all of these are fundamentally sampling operations. Scientific simulations in biology and chemistry, drug discovery optimization problems, these are all areas where you're inherently working with probability, uncertainty, complex distributions. Extropic envisions a hybrid future where a conventional process handles the deterministic logic while a TSU chip handles the sampling. The two working as co-processors, each doing what they're actually built for. Now, what do I think? Well, I genuinely think Extropic is onto something real here. We have spent 70 years engineering noise out of computers, and now we're using those computers to spend enormous energy faking noise back in for AI. That is an absurd situation, not gonna lie, and something was always going to point that out. Now, sure, the execution challenges for Extropic are real, the software ecosystem problem is real too, but the core idea that the right hardware for probabilistic AI is hardware that is physically probabilistic is one of those things that, once you understand it, feels completely obvious in hindsight. And I find that kind of clarity genuinely exciting. Computing doesn't end here. It just finally starts making sense.